Let us discuss a problem from theory of machine here. Basically, you have a cantilever beam and a spring is attached at the right end with a mass on it. So basically, we need to find out remember that the cantilever beam is massless. It's only you have to consider this cantilever is just like an elastic member. So we need to find out the vertical oscillations of this mass. Okay. Now here one thing you have to understand that when you apply a load on mass P, this load propagates through the spring as well as the same load is getting applied at the cantilever end of the beam. So it's like more or less the same. This load actually because of this tensile load, or this load will act as a tensile load on the spring will stretch, and the same load P gets applied at the end of the cantilever beam, and the beam will also deflate. So it's the same load that is passing through the spring as well as the end of the cantilever. So as I told you that cantilever in all these kind of problems is considered as a elastic member with zero mass. So if you, because of this load, there's a deflection like this. So I can more or less consider at this point B, I can more or less consider a beam as a spring which on the application of load P deflects by this much amount as the beam would deflect, okay, by the application of load. So the summary of this is that beam can be considered as a spring, okay, and there is a spring already attached, okay, which is K. So these two springs are in parallel, are in series, sorry. And this series thing you should understand only how the load getting. See, remember that in a series the load is same through for each of the spring, and the same thing happens here. The load on bottom spring is P, and the load that is getting applied on the end of the cantilever is also P. So it's more or less in a series. So once you decide this, now the natural frequency of the mass is nothing but if you convert into a single equivalent spring, so K equivalent by mass. So K equivalent for this will be K equivalent for us when the two springs are in series. It's basically 1 by K equivalent is 1 by K1 plus 1 by K2. So K beam plus K. Okay, now we need to find out K beam. Okay, so but let's write down here that K. So from this formula, it's in series. Okay, so it is KB into K by KB plus K. Okay, so now how do I get KB? So KB is basically when you apply a load at the end of cantilever beam and it deflects by delta, then so what is this delta in terms of P? Now from the deflection of beams you will see that when you have a cantilever beam and a load P is applied at the end, the deflection is PLQ by 3EI. This is again derived from deflection of beams by just integrating double integration method. M is equal to EI d square y by dx square. So by that method even you derive. So this is something which you got to remember for this vibration problem. So the K beam will be load plus deflection, so P by delta. That's what classical definition of stiffness means. So it is 3 EI, where I is mass moment of inertia, E is Young's modulus. So KB is something which we got. Similarly, you can get for, like, if the spring is attached at the middle and it's a simply supported beam, then you have to appropriately the delta in terms of P will change. So this formula is only for the cantilever beam. So once we got this 3EI by L cube as the beam, so and the secondary spring is K only. So now you have to just substitute it here. Okay, so K equivalent is 3 EI by L cube into K by 3 EI by L cube plus K. So I think L cube will get cancelled. So 3 EI K by 3 EI plus K L cube. Okay, so this is K equivalent, and therefore the omega will be K equivalent by mass. Okay, so 3 K by mass m by 3 plus K L cube. So this is very simple problem. Only the idea is how do you convert this system. So let's see the answer. The answer is obviously A. Okay, so this is a very simple problem. Only thing is you have to convert into set of springs and then apply the root K by M formula. Thank you. Answer is A. Thank you.